All right. Happy Tuesday, week 6. Woohoo. We are week 6. This is the second to the last chapter, or my favorite word, the penultimate chapter. So we're going, I love that word. It's just such a good word. So we're going to do 9.1 today. We'll do 9.2 and the lab on Thursday because the lab fits really well in with 9.2. So today we are only going to be dealing with proportions. We're going to ignore mean today for the most part. We'll use the word mean, but we're pretty much ignoring mean today, and we're going to deal with proportions. So we're going to obtain a point estimate for population proportion. You already know how to do that. We did that Thursday. We did that previously. We're just going to kind of do that again. Then we're going to do something called a confidence interval. And confidence interval with a margin of error is like if I said that somebody had 46% of the vote plus or minus 3%. That's what a confidence interval is. And I'm going to explain the intricacies of that. We're going to do the math, and I'll give you a fun new calculator function. And then also what we're going to do is if you want a specific margin of error, we're going to do math to determine what the sample size you need to have in order to get that specific margin of error. So that's what we've got today. It really shouldn't take very long. I would be surprised if it goes past 45 minutes. So probably even less than that. This is a pretty short section. It's, as I said, I'm going to dial things back a little bit because I want you to focus on your final project and not have as heavy of a homework weeks or anything. So that's why we front loaded everything so that you have most of the math you need so you can work on those final projects. But I believe this Thursday, the data is due for the final project. You don't have to do any math with it. I'm not expecting any graphs. I'm not expecting any tables. I just want the raw data. And then there's 2 prompts I want you to respond to, and they should be pretty quick and easy. And so the data itself, the raw data is 10 points, and then each of the 2 prompts are 5 points each, and those go towards your lab grade. So if your lab grade was a little lacking, or if you're just a perfectionist who wants everything perfect, I'm not speaking to any of you. There's nobody in this Zoom meeting who's a perfectionist at all. Anyway, um, then so if you want perfect scores, and I mean, this is a pretty easy way to get some points, really. And if you're collecting this data and you're like, this is really not working, I'm not going to be mad at you if you switch your topic. It's not set in stone until you turn that final project in. It could even be you give me this assignment, this data, and then next week as you're working on your project, you're like, this is just not working for me. And you could switch it then. You don't even have to inform me. Just do it. I'm not going to be mad at you. All right. So let's get going. Uh-oh, maybe. Okay, we know what a point estimate is. Point estimate, it's a statistic that's going to estimate our parameter. Remember, a parameter is population, statistic is a sample. So you just take the number of successes or the number of individuals that have a certain characteristic and divide it by your sample size. We've done this before. This isn't new. And I'm not going to do this example because we know how to do this. Okay. All this is just calculating a point estimate. We've done this so many times. Okay, so let's talk about confidence intervals. So what we do is if we are sampling, so sometimes our population is too big to question everybody, or we don't have access to the entire population. So we can take a sample and we can make estimates based on a sample. But you can't just say, if my point estimate was 53%, I can't just say about 53% of the population. You have to give me a margin of error. So based on the sample size and how confident you want to be, whatever confidence level you want to use, we can have a margin of error. So you probably have seen it in betting. You've seen it in presidential polls. So if I said something like somebody it has 46% of the vote plus or minus 3%, then it could be as high as 49. It could be as low as 43. It is somewhere between there. So a level of confidence, what that is saying is that I am like 95% confident. So what it means is that if I constructed 100 confidence intervals, 95 of those would actually contain my population proportion. So whatever the true population proportion is, which I don't know what it is, but whatever the true population proportion is, if I took 100 different samples, created 100 different confidence intervals, 95 of those confidence intervals would contain my actual population proportion. So I could have, there's several, I could be super confident, could do a 99% confidence level, or I could do an 80%. It could be any value. And there's technical ways we choose this, but you're just going to use, you just choose one or whatever they give you in your homework. So some people will do this in their final projects. They will construct a confidence interval. If they're doing something that is categorical, and they take a population, let's say they're looking at left-handed, right-handed, and let's say 12% of their sample are left-handed, then they can construct a confidence interval to make an estimate of what the population is of left-handed people. So you can do this in your final project if you want. I think I've only ever had 2 people do it, but it actually turned out pretty nice and I liked it. I was using the stuff at the very end of the term generally makes me smile, and you want the person grading your project to smile. So if you want to do it, go for it. If not, not a big deal. You're not going to get dinged for not doing this. Okay. So here's an example of the level of confidence. So if I say, for example, I have a 95% level of confidence, then my alpha is 0.05. We're going to be using alpha a lot. So as I just said, what this implies is that if I have 100 different confidence intervals, 95 of them would be expected to contain the population proportion. So what this is saying is that, remember the alpha is the probability of making a type 1 error. So that 5% right there is the probability of my confidence interval not containing the population proportion. That's basically what that's saying. That there's a 5% chance that the confidence interval that I created doesn't contain the actual population proportion. This is one thing I don't like about presidential polls is they will give you margin of error and they will give you and they'll give you their sample, but they won't tell you the confidence level. For all I know, they have a 50% confidence level. I don't know. They don't tell us. So that's kind of a struggle for me when I see those things. I'm always looking at their graphs to see if they told me what their confidence level is, and they never do. It's rude. So rude. Okay. The way that we write a confidence interval, there's actually 2 different ways that we write it. One of the most common ways is you would put whatever your point estimate is plus or minus your margin of error. So this is the most common way that we see it. So you'll say they have 46% of the vote plus or minus 3%. So this is helping us to figure out how accurate is our point estimate. But this is one of the more common ways to write it. The other way that we write it would be to put it as an interval. So my point estimate would be flat in the middle. So this would be the p hat minus the margin of error, comma, p hat plus the margin of error. We would put those there. So we would actually calculate the upper and lower bounds. So if I did 46% plus or minus 3%, then this would be 43 or 0.43 and 0.49. It would give us the upper and lower bounds of my confidence interval. So those are the 2 different ways that we list them. And your homework's going to have you do it both ways. Someone have a question? We're doing okay so far? Okay. You holler at me if you have a question. I'm not trying to rush. We're going to get to the math in a minute and I'll slow way down. Okay. So there's 3 different things that are factors that our margin of error depends on. First thing is our level of confidence. As the confidence level increases, as the level of confidence increase, the margin of error is also going to increase. So if I have a 99% confidence level, my margin of error is going to be bigger. But then if I, like, for example, I had 95% confident that I'm at 46 plus or minus 3%. Well, now if I'm 99% confidence, I might be plus or minus 9% or 6%. It's going to be larger than that 3. So sample size. If I get a larger sample size, as the sample size increases, my margin of error is going to be smaller. Obviously, larger sample sizes are going to be more accurate. Therefore, I'm going to have a smaller margin of error. And also, as my standard deviation gets larger, my confidence interval is going to get larger. So, because the more spread we have, the wider the interval. And that makes sense because if my data is very spread out, then so obviously this is for quantitative rather than categorical. You can use confidence intervals for both of them. But standard deviation, if I have a big standard deviation, I'm going to have a larger confidence interval. Questions on any of this?
I have a question real quick.
Yes.
It's on the last slide. I missed so it's the proportion plus or minus, and it was
Yeah, so if I have
0.43 and
so if I have
0.49.
0.46 plus or minus 0.03, so
Mhm.
let's say that this is what so this right here is my point estimate, my p hat, and then this right here is my margin of error. So I just subtracted 3% to get this, and then added 3% to get that.
Okay.
So this is just two different ways to write it. So the
Uh,
point estimate is smack dab in between those two values.
okay. Yeah, I was wondering where those numbers came from. I guess I just missed that. Sorry about
No,
that.
no problem. No need to apologize at all. Okay. So this is a reminder that so this is the same thing. This is from section 8.2. This is kind of a carryover from 8.2. So our sample, if we're approximately normal, then we're going to use the proportion that we have for our mean. And our standard deviation, we calculate like this. This is exactly what we did in 8.2. And we use this if NP times 1 minus P is greater than or equal to 10. Also, every trial has to be independent. So our sample has to be less than 5% of the population. These are the conditions that need to be met. So if it asks you what conditions need to be met, these are the conditions that need to be met. That's just if my open math asks you that. So I'm just letting you know.
What do you mean by conditions that need to be met?
In order to do the math that we're doing, these things need to be true. Whoops. So this needs to be true, and this needs to be true in order
Oh,
for us to do this math.
okay.
Yeah,
Thank you.
you're welcome. And in your homework assignment, if it doesn't say these things, don't worry about it. But it might ask you, were the conditions met? And in order to answer that, you would do this right here, this NP times 1 minus P, make sure it's greater than or equal to 10. And then you would state that our sample size is less than 5% of the population. So just make sure you make that statement. I don't remember if it's asked or not, but I don't remember if it's this unit or next unit. It's either asked or it might have been 8. It's 8, 9, or 10. One of them asks you that. I don't remember which one. Okay. So the way that we find our margin of error, I'm going to circle just the margin of error piece. This right here is the margin of error piece. Okay. This is a z-score. And this z-score is because a confidence interval is a center. So I'm going to put this like this. A confidence interval is a center. We cut the alpha in half. So remember the alpha is the percent or the probability that that my confidence interval is does not contain the population proportion. So if I have a 95% confidence interval, we have to cut what's left in half. So I have 2.5% here and 2.5% here. This should look familiar. That's why the z-score is based on alpha divided by 2. Is because we're looking at that center. This in here is my confidence interval in here. All the stuff in here is where possibly my population proportion is. So I take the z-score for that boundary. So I would take the z-score for this right here. I would take the z-score for that right there, which is at alpha divided by 2. And then I'm going to multiply it by the standard deviation. That gives me my margin of error. Because basically what I'm saying is it's this many standard deviations away from the mean is the boundary. So I take standard deviation and I multiply it by that z-score. And if I subtract it from p hat, I get the lower bound. Add it to p hat, you get the upper bound. And obviously these things right here. Once we're doing the math, it's going to make more sense.
Are we multiplying z-score by alpha divided by 2?
No, it's z-score, z sub alpha divided by 2. So it's saying find the
Okay.
z-score of that alpha divided by 2. That's basically
Okay.
what it's saying. Yeah, it doesn't show up really well that it's a subscript. It's kind of ugly.
Thank you.
It's easier when you write it. That looks more like a if I write it big, it looks a little bit better. Yeah, it's a sub. Kind of like when we do mu sub p hat or sigma sub p hat. Yeah, it's a subscript. That's an ugly hat. Okay, gonna do some math. So it's the z-score of this spot right here of your boundaries. Woo! It's the positive z-score of these boundaries right here. That's what it is. So it's yes. See, but it is the z-score of the boundaries. So of that 2.5 or whatever. Yes. And then yes, exactly. Yes. Yes. And then when we're doing we're gonna when we get to mean, it's gonna be totally different. I'm gonna ignore mean. We'll get to that on Thursday. All right, let's move on. This is exactly what I just drew. Mine's prettier. So this Z sub alpha, so I'm gonna write it. This right here, it's called a critical value. We call it a critical value because it is the edge of our confidence interval. So anything outside of that is a critical region. Like there's error, Will Robinson. So it's called the critical values. The critical values are the edges of my confidence interval. So when they ask you for a critical value, they want that z-score. And it represents the number of standard deviations we can be from the mean and still be within my confidence interval. It's going to make more sense once we math it out. It's always easier once we have the numbers there. Okay. Okay. At the bottom of your Z table, so this is just a snip of the bottom of your Z table. These are the most common critical values. And these are alpha divided by 2. Uh-oh, I think my baby's here. He didn't call me. He just sent me a picture. Hold on. I'm sorry for you guys at home. Oh my gosh, she's gorgeous.
I want to see.
I'm going to show you guys just a second. I have to tell my son that.
Congratulations.
I will show you guys.
Whoop, whoop. Congratulations.
Oh,
Isn't he beautiful?
oh my gosh.
Okay.
Super cute.
Okay, I gotta say, what's his name? Name and his details. Okay. He's 8 pounds, 5.1 ounces.
Well, he was a big boy.
Yeah. Uh, my son was 7 pounds, 8 ounces, but he was 3 weeks early. Just a second. Or FaceTime after. Okay, there we go. I just asked him if I could FaceTime after. Okay, sorry about that. Sorry about that, folks at home, but grandbabies are really important. I'll tell you his name if he texts it to me. Okay, so these are the most common critical values, and I have a hair on my screen. Doggone it. Okay, so if you are using anything different, if they say any, if you get any, thank you, Maggie. Thank you, Natalie. Thank you. Who else? Thank you, Andrea and Hannah. Okay. So I'm like flustered now. So if you get something else, you're going to need to use inverse norm. So for example, let's say that I wanted an 85% confidence interval. I am going to take 1 minus 0.85, which is going to give me 0.15. And then divide that by 2. Obviously, I could do this in my head, but I'm a little distracted. And that's 0.075. This is what you're going to do your inverse norm with to get your z sub alpha divided by 2. But you want the positive z-score. So whatever it is, just use the positive z-score. But this is what you are going to put in your... My daughter just got the picture too. Okay. Anyway, so put that in your calculator, inverse norm, that's your critical value. This is nice though. It's nice to have this for like just quick reference, since you all printed it off anyway, right? His name is Ezra. And you know what? That's the name I guessed. Well, when I took my son out for his birthday, he told me that that was the name they were leaning towards. So, what a great name. What a great name. All right, let's move on. I gotta focus, Claes. Okay, moving on. Okay, so we're interpreting the confidence interval. So the interpretation of the confidence interval is that if I took a whole bunch, I already told you this, we're going to do it again. If I took a whole bunch of confidence intervals, created a whole bunch of confidence intervals, then 95% of them, or whatever our confidence level is, that's how many will contain the actual population proportion. And I don't know how they came up with the math that they did, but they came up with the math that they did. So let's math it out. Let's actually do some here. So in July of 2008, a Quinnipiac poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. We're going to obtain a 90% confidence interval for the proportion of registered voters who are in favor of the death penalty for people convicted of murder. Okay, so I'm not going to deal with our conditions. We're going to do that on the next page. I'm going to go back here. Well, I'm going to go back here and I'm going to see that 90% has a critical value of 1.645. So I'm going to write that down here. So my z sub alpha divided by 2 was 1.645. Okay. And we need to calculate the standard deviation. So my standard deviation sub p hat equals square root of, I need to get my p hat first, 1123 divided by 1783 is 0.63 is what I'm going to call it. Okay, so we have 63%. So I'm going to do 0.63 times 1 minus 0.63 divided by our sample size, which is 1783. Okay, so point, so it's 0.63 times 0.37. That is right, yeah. Divided by, I need parentheses, sorry. Divided by 1783. Okay. So this right here is 0.0114. I don't know why I went out to three places. All right. So I have my standard deviation and I have my z-score. So to get my margin of error, and margin of error is going to be 1.645 times 0.0114. I got 0.019. So my margin of error is 0.019. So in order to create my confidence interval, I'm going to take 0.63 plus or minus 0.019. Did I math that out correctly? It looks like it. Okay. So this is my confidence interval right here. The other way to write it would be to write it. So I'm going to take the 0.63 minus 0.019, and I have 0.611. Then I'm going to do 0.63 plus 0.019, and I have 0.649. This is the other way to write the confidence interval. So the way I would answer this, I would say we are 90% confident that the actual proportion of people who are in favor of the death or who are opposed of the death penalty, wait, is this favored? Oh, are in favor of the death penalty is between 0.611 and 0.649. I'm going to show you it all nice and pretty typed out, but before I do that, are there any questions? Okay. This is how the textbook does it. So first things, we have, here's my conditions. We tested my conditions. They're all nice and pretty. NP times 1 minus P is greater than or equal to 10. Our sample size is less than 5% of the population. They found their Z sub alpha divided by 2. And I don't know why the rest of the math's not on here. It disappeared. It was on here earlier. All right. So here's my, it rounded it to 6.65 and 0.61, but that's fine. We're 90% confident the proportion of registered voters who are in favor of the death penalty is between 0.61 and 0.65. I'd be okay with you saying 63% plus or minus, is it 2%? 2%. I'm okay with you answering it like this. If you were taking a test and you answered it like this, 100% you'd get credit for it. Questions before we move on?
Where's the 2% coming from?
Because my margin of error is right here. I just rounded it to 2%.
Oh, okay, so it's all coming from this
Yes.
example. Okay,
Yes.
thank you.
You're welcome. Anyone else?
So
Right.
how does the 90% come into the equation? Like, where do we
The
use
Z
that?
score. That's the Z score.
Okay.
Yes. That's the only place we see it. It determines how many standard deviations away from the mean we can go and be 90% confident and capture 90% of the situations or the samples or whatever. So it tells you how many standard deviations away you can be. So take a look here. So remember, as I said, that your confidence gets greater, your margin of error gets bigger. So if I'm 90%, I can be 1.645 standard deviations away from my proportion or my mean and still be within my confidence interval. If I go down to 99%, I get down to 2.575. So that's almost 3 standard deviations away. It's more than 2.5 standard deviations away from my confidence interval. That's further than outliers right there. That's like capturing some of those outliers. So I almost feel like a 99% confidence interval is almost meaningless. 90 is good. 90 is pretty. 90 or 95 is generally where we go, but you're going to end up with huge margins of error unless your sample sizes are gigantic. All right. Okay. So let's do another one. The Gallup organization conducted a poll in which a simple random sample of 1,016 Americans 18 and older were asked, do you consider the amount of federal income tax you have to pay is fair? Of the 16 adults surveyed, 558 said yes. We're going to obtain a 95% confidence interval. So let's find p hat first. Everybody go ahead and find your p hat. What I'm going to do is I'm going to have you do the whole thing, but I'm going to piece it out and say find this and then find this. So go ahead and find your p hat. Did we all get about 55? Okay. Go ahead and find your standard deviation. I'm working quietly on the screen, so if you get stuck, go ahead and look up. And I'm going to round it to that. One thing I love about our curriculum is you've already had practice calculating that standard deviation in the last unit, so it's not as scary. So go ahead and find your z sub alpha divided by 2. You can use the z table, or you can use your calculator if you want to with your inverse norm. Okay. Is that right? Okay, so I have how'd we do? Questions?
Up here where the sigma's at, the 0.55 times 0.45.
Yes.
Where did the 45 come from, and why did we do it like that versus the other way we just did it?
It is the same way. I just did 1 minus 0.55. So 1 minus 0.55 is 0.45.
Oh, okay. Threw me off. Okay.
I almost never write it this way because every time someone asks that, and it's like I confuse people every time. Sorry about that.
It's okay. Thank you.
No problem. Anyone else? So this is the answer. It's either this or that's ugly. Let's not do that. Let's do yellow. So it's either this or this. Did we do okay? We get there? Any other questions? Right. So I'm going to give you the calculator function now. So in your calculator, this is the function. Go ahead and write it down, and then we're going to go to the calculator. And the calculator is going to be so lovely for you. You're going to be pleased as punch, as they say. All right. So let's go to the calculator. So if you do second, oh, that's not what I want, clear. Do hit the stat button and go over to tests. So hit stat and go over to tests. And we're going to one prop Z interval. So you're going to have to go down a little ways. So what this is one proportion Z interval. That's what that stands for. One proportion Z interval, and then hit enter. So it asks you for our number of, look at that, it's already, no, it's not. Asks you for your number of successes. So my number of successes is 558. My sample size, is this it? It's 1016. And then my confidence level is 95%. So you put in your number of successes, your sample size, and your confidence level. That's all you need. And when I hit enter, it'll give me the p-hat, and then it gives me the interval. So if you want to know the actual margin of error, you're going to have to do a little bit of math. You're just going to take this upper value and subtract the p-hat to get the margin of error. So if I took the, let's see here, 0.57981 minus 0.5492. Well, as soon as I start typing in the calculator, it's going to disappear. So I had to write it down. So if I do 0.5781 minus 0.5492, I'm going to get the 0.289, which is what we got for our confidence interval. Close enough. We got, wait, on my margin of error, that's not right. That's not what we got, was it? I have 0.581. Let me go back there. Let me go back there. That's not what I want to be. What the heck am I doing? Go all the way down. One prop Z in. There we go. I think it's just rounding. Why do I do that?
What's the second function on the calculator
What do you mean the second function?
to get to that
You just hit
second what?
stat. You could just hit stat and then arrow
Oh,
over to tests. And then you
gotcha.
just scroll down. Okay. You go back here.
I think you just mistyped one of the numbers
Yeah.
is why you got it different, because I did it in my calculator and it's the same.
Exactly what I did. I mistyped it. So yeah. So should get the same thing. So yeah, use your calculator. I love doing it by hand. Yeah, that's what I did wrong. I forgot the 9. Thank you. So just use your calculator. I mean, I love doing the math by hand, but use your calculator. So on your homework, you are going to be given what they're going to do. They'll give you a confidence interval. Let me just clear this off and get rid of all of this. So they're going to give you something. This does not pertain to this problem. I'm just using this green. So what if they gave you something like 0.45 comma 0.52 and they want you to write it like this? So they will tell you, take this interval and write it like that. What you need is you need the halfway point to get your p hat. So what I would do is I would do 0.52. 0.52 minus 0.45, which gives me 0.07. If I divide that by 2, I'm going to get my margin of error, 0.035. This would be my margin of error. And then just subtract that from the 0.52 to get your center. If that makes sense. Because you're looking for that halfway point. Because my p hat is somewhere in here. This is your p hat is somewhere in there. That was really ugly. My p hat will live some smack dab in the middle. So you need to find that middle number. Then you find the difference between the upper value and that middle number, and that gives you your margin of error. Okay. Now we're going to work backwards. We have a margin of error. We want to know our sample size. That's the next thing we're going to do. I already got that. Okay. So the problem with the problem is that we need to have a p hat in our calculations. If we don't have a sample size, we don't have a p hat. So there's two different things that we can do. So this is the formula. So the formula is p hat times 1 minus p hat times the z-score, the critical value, divided by the margin of error squared. This is the formula that we're going to use. So the problem is we don't know what our sample size is, therefore we can't have a p hat. So what we need to do is we need to have a prior estimate. There's two different ways to do this. So we will either use a prior estimate. So basically, let's say I took a poll last week and I determined that I'm making stuff up. This is a presidential year, so I'm making stuff up. I took a poll last week and it was determined that Kamala Harris had 43% of the vote. I can use that prior estimate. Even if it's not completely accurate today, it's going to be somewhat close, right? It's not going to be huge. It's not going to be, oh, now she has 15% or now she has 85%. It's not going to be that different. So it is it's accurate enough for us to do this study. If we don't have a prior estimate, use 0.5 as your p hat, because this is going to give you the largest possible value. This is going to give you the largest value of n you possibly can need. But using a prior value is going to be better because it's going to result in a smaller sample size. And we don't want to have a sample size any bigger than we need to, right? So let's do the math here and you'll see. Okay, okay, all right. So a sociologist wants to determine the percentage of residents of America that only speak English at home. We want to know the sample size that we need to obtain if we want within 3 percentage points within 95 or 90% confidence interval. So in 2000, the survey showed this right here was our percent. So we're going to use this as p hat. So my formula, n equals p hat times 1 minus p hat times z sub alpha divided by 2 over the margin of error squared. So the p hat that we are going to use is 0.824. My z, we find that on the z table. I'm going to go back a few screens. I don't remember which margin of error we're using. Are we using 95%, 90%? Ugh. I can't get back there. 90%, I wish I had it up on my screen. 90% is 1.645. Go all the way back. Okay, here we go. So we're going to use 1.645. And my margin of error is 3 percentage points, so 0.03 squared. You should be able to put this entire thing into your calculator. Put the whole thing into your calculator. I did something weird because I have a negative value. Okay, let's try it again. 0.825 times 1 minus 0.825. Oh, that's what my problem is. I didn't use parentheses. Times parentheses 1 minus 0.825 times 1.645 divided by 0.03 squared. There we go. So I got n equals 434.09. Now here is the trick. Here's the deal. You always round up because sample sizes have to be a whole number. You can't sample a 0.09 of a person. 434 is not enough because it is smaller than this value. Always round up. I'm going to write this largely here. Always round, that's an R, up. Always round up. Therefore, the n that we're going to use is 435. Even if it's as small as 0.09, always round up. One of the examples that I like to use in this case is, let's say that I have 170 students and every bus can only hold 50 students max. I am not going to only order 3 buses. I have to order the 4th bus. Even though it's only 20 kids, I have to order that 4th bus because 3 buses is not enough. Even if I had 152 kids, if I can only have 50 kids on the bus, I've got to order that 4th bus. So it doesn't matter how small that little bit is over the 434, you have to round to 435. That's my sample size. Questions before we do another example? Let's be like our last example. I think we're just about done.
For
Question?
the 0.03, what does the E represent?
That's the margin of error.
Oh, okay. Within the percent. And that's the 3%
Yes.
percentage?
Yeah,
Oh, okay. Thank you.
you're welcome. Okay. See, I think we would have been in the 45-minute mark had I not had a baby been born.
I feel like, I'm sorry, I have a question.
Oh, go for
I
it.
feel like I missed something somewhere with the ZA/2.
So this is the critical value. I got
Mm-hmm.
this right here. This is for the 90% confidence interval.
Mm-hmm.
So you just find that Z-score.
Okay, so that's just a Z-score. Okay,
That's just that critical Z-score
gotcha. Thank you.
based on the 90%. So basically what this is, this formula is, all it is working the other formula backwards. I need to go back. Okay. It's working the other formula. So if I have my, it's this form, so it's just this formula backwards. We're just undoing it. So Z times. So it's just all I did was solved for all I did was solve for solved for n instead. That's all I did. That's the only math that was done here is I just basically, okay, I square everything. Now I have E squared equals Z squared times P1 minus P over N. multiply both sides by n. Now I have n e squared equals z squared. And then now what I can do is I can divide by the e squared. So I'm not going to continue, but if I just did all of the math to solve for n, this is what you get. This is what you get. This is the same thing. Because once I divide by e, now I have n equals, I guess I am going to do all the math, 1 minus p times z squared over e squared. And I just moved the square to the outside. All it did was rearrange the formula so that you didn't have to. So it's the same formula. It's just, so I'm sorry, I get like crazy about the math. So we would need, did I math it wrong? It's 435, unless I mathed it wrong. 435.
I heard you saying 0.825
Oh,
is
Yeah, you put
0.84.
825, yeah.
you know, you gotta stop me when I'm doing it wrong.
Sorry, I was trying to keep up.
It's okay. So,
I got
Same.
436.04 and rounded
yeah.
to 37.
Same, I got 436. I just didn't want to correct you.
Please correct me. Please correct me. There we go. If you don't correct me, then I don't know I do it wrong. I make more math errors than anyone because I'm doing math all the time. Just correct me, please.
I was
Okay.
just still trying to wrap my mind around other stuff.
It's okay. Everything was correct except for I threw a 5 in there instead. All right. So we would need 437 randomly selected American residents. So the next one we're going to do, I'm going to do it both ways. I'm going to do it with a previously done survey, and then I'm going to do one without so you can see the difference. Maybe if I can get to that screen. All right, this is our last page. We are done after this. Okay. So an economist wants to know if the proportion of US population who commutes via carpooling is on the rise. So we need to figure out our sample size. If we want within 2 percentage points, we're going to use a 90% confidence interval, which is great because that is a 1.645. This is what we had on the last one, so that's why I know that. And we previously, in 2009, we had a 10% estimate. So we're going to use that. I would like you to try this. I'll do the last one. I would like you to attempt this with the formula. I'll work quietly behind you. So go ahead and start the formula, and I'll work quietly behind you. To make sure I actually put it in my calculator correctly this time. How'd we do? I got 609 people. Okay. So now we're going to look at if the economist didn't get any prior estimates. So he doesn't have any prior estimates or for some reason doesn't want to use them. So remember, in that case, you will just use 0.5 as your p hat. So we're going to do this again using 0.5 as my p hat. Okay, so go ahead and put that in your calculator. Look at the huge difference. You'd need more than 1,000 people more if you don't have a prior estimate. That's crazy. It is absolutely crazy. This is why using a prior estimate is a good idea. So for example, let's say you are doing you're doing, I don't know, I can't even think of anything, but you're doing your final project on something that there are studies out there that other people who have studied it. You could always grab one of theirs and then use your data to create a confidence interval or to determine, say, in order to make this true confidence interval, if I wanted it to be within this margin of error, I could have taken a sample size of this. You don't have to do that. I'm just saying, these are things you can do. I mean, I can come up with ideas like any assignment we've done. I can come up with ways to use it on a final project. But also you got to remember, I've been teaching this class for quite a few years. So I've been teaching this particular class for, I think, 5 years now. So I obviously can come up with lots of things. You don't have to use everything we've done. If you just have a couple of really good if you've just done a couple of good, solid things that has answered your question, and some nice, pretty visuals, you're going to be fine. All right, so that is it for this lesson. Questions on this lesson specifically? Okay. Anything not on this lesson that you need just for while we're on recording, something that somebody else might want to hear or hear the answer to? All right, I'm going to turn the recording off.